Welcome viewers to the fifth segment of the seventh lecture for the online series of lectures for the course of linear algebra. Towards the end of the previous segment, we raised this question about invertibility of a linear operator T on a vector space V. Okay, so let me write this question again here in this segment. For which linear operators T on the vector space V uh, does there exist a linear operator T inverse such that T composed with T inverse is equal to T inverse composed with T is equal to the identity operator on V. Okay, so to answer this question we need more general definition that I'll be giving now. So suppose there is a function T from the vector space V to the vector space W. We call this function is called invertible. It's just a function between these two vector spaces, and we'll call this function to be invertible if there exists a function. Okay, it's a more general definition. We don't attach the linearity property here to this function. Okay, so it's just a function, a naked function, so to say, between two vector spaces V to W, and this function would be called invertible if there exists another function um, denoted by U from W to V such that U composed with T is naturally a function from V to itself, right? So we want this a composed transformation or function from V to itself to be the identity function on V. So this is the identity function or map on V, that is U composed with T is equal to I sub V. Okay, and we also want T composed with U, which is naturally a map between from the vector space W to itself such that T composed with U and TU from W to itself satisfies TU is equal to the identity map on the vector space W. Okay, so if these two equalities are fulfilled, we say that the function T from the vector space V to the vector space W is invertible. Okay, and one should be able to verify that if T is invertible, the map from V to W, if this is invertible, then this function U that is required to meet its definition is unique. Okay, and we should give a name of this unique function from W to V. It's called the inverse function of the given function t from V to W. Okay. And we denote this inverse function u of t by u of t is denoted by t inverse. Okay, so the inverse u of t is denoted by t inverse. Okay, so furthermore, uh, t is invertible. T is invertible if and only if 1 t is 1 to 1. Okay, how do we state this mathematically? TV is equal to TW implies V is equal to W for all V and W in the vector space V. Okay. 2, T is onto, right? That is, so remember T is a function from V to W, and T is onto means that the range of T is all of W. In other words, if I pick any W from the vector space big W, there is always a pre-image of that vector W in the vector space V under T. So let me write it. That is the range of T is all of W. Okay, good. Now we get to the special case when this linear operator, where this function V from W, from the vector space V to the vector space W is linear. Okay, so let me erase everything. So for that, in that situation, we have the following theorem called Theorem 6. Let V and W be F vector spaces. They are both vector spaces over the same ground field, vector spaces, and let T be a linear transformation. We want it to be linear from V to W if this guy T is invertible, then the inverse T inverse is also a linear transformation from W to V. Okay, so we need to prove that T inverse, the linear transformation the inverse of the linear map T is also a linear transformation. Okay, proof. Let V1, V2 be two arbitrary vectors from the vector space W, okay, and C is any scalar in F be a scalar. We want to show that the following holds. T inverse acting on CV1 plus V2 is equal to Ct inverse of V1 plus T inverse of V2. So that would mean that the transformation T inverse from W to V is a linear transformation. Okay, so let's prove it. So let U1 is equal to T inverse of V1. So we know that T inverse is a one-to-one and onto map, right? Since T is a one-to-one and onto map, so if I pick up any two vectors um, from the domain of T, from the codomain of the linear of the linear transformation T, then that those two vectors will definitely have pre-images um, in the vector space V under the operator T, and that would mean that we'll always be able to find a vector U1 such that U1 is equal to T inverse of V1, and we also let U2 to be the vector in V such that U2 is equal to T inverse of V2. Okay, so this means that the vector U1 is the unique vector in V. U1 is the unique vector in the vector space V such that T of U1 is equal to V1, right? And similarly, this implies that U2 is the unique vector in V such that T of U2 is going to be equal to V2. Okay. Why is it so? Because T is one-to-one. Okay. All right. So now from the linearity of T, from the linearity of the transformation T, it follows that T of C U1 plus U2 is equal to C times T of U1 plus T of U2. Okay, and T of U1 is equal to V1, sorry, C times V1, since T of U1 is V1, and T of U2 is V2. Now, so we have been able to show that T of C times U1 plus U2 is C times V1 plus V2. Okay, now since T is one-to-one, which follows from the invertibility of T, C U1 plus U2, okay, is the unique vector in V. There cannot be two vectors here for which the image of T would be CV1 plus V2 since T is 1 to 1, right? So this vector is the unique vector in V which is sent to this vector in W, which is sent to CV1 plus V2 in W by the linear transformation T from V to W. Okay, I need some space. Okay, so this vector, this guy is the unique vector that is sent to this vector under the linear transformation T from V to W. Hence, T inverse of this guy, right, C V1 plus V2 would be equal to this vector CU1 plus U2. Okay, so that T inverse is well defined, right? CV1 will be mapped to that unique vector. Okay, that unique vector of the vector space V. And by definition, U1 was taken to be by hypothesis, U1 was taken to be um, uh, T inverse of V1, and U2 was T inverse of V2. So, which proves that T inverse is also linear. Okay, and T inverse is linear. QED. Okay, so now I need to define non-singular linear transformation. Okay, definition. A linear transformation T from the vector space V to the vector space W is called non-singular if TV is equal to the zero vector of the vector space W implies the vector V is identically equal to the zero vector of the vector space V. That is, the null space of T, kernel of T is equal to the singleton containing the zero vector of the vector space V. Okay, so that's the definition of non-singular linear map. Now, fact about this definition, which will show that non-singularity is equivalent to one-to-oneness of the linear transformation. Okay, let T from V to W be linear, then T acting on this vector U minus vector V, okay, is nothing but Tu minus Tv, follows from the linearity of the transformation T from V to W. Okay, hence Tu is equal to Tv is equivalent to the fact that T of u minus v is equal to the 0 vector of the vector space W. Okay. Now, a linear map T from V to W is 1-to-1 if and only if whenever for linear T one has Tu is equal to Tv for any uv. So whenever one has this equality, it implies, let me write in words, it implies u is equal to v. That's the definition of one-to-oneness of a linear transformation between two vector spaces, right? So then this is equivalent to the fact that so uh, so this is equivalent to T from the linearity. I use linearity to write it like this, right? Is equal to the 0 vector on the vector space W. And that would imply this a vector u minus vector v is equal to the 0 vector on the vector space V. Okay. So this implies that this argument is the 0 vector on the vector space V. So in other words, T is non-singular. So we just have seen that a linear map T from the vector space V to W is 1-to-1 if and only if T is non-singular. Therefore, let me write the result. T from V to W is a linear 1-to-1 transformation if and only if it is non-singular. Okay, good. Now we have a theorem, okay, which is theorem 7. Let me state the theorem first and then I'll prove it. Theorem 7. So a while ago we have seen that non-singularity and one-to-oneness of a linear transformation are equivalent. Let T be a linear transformation from vector space V to the vector space W, then T is non-singular if and only if T carries each linearly independent set, subset, linearly independent subset of the vector space V to a linearly independent subset of the vector space W. Okay, so let me prove this result. First, suppose that T is non-singular. T is non-singular. We need to prove that T takes a linearly independent subset of V to a linearly independent subset of W, right? And let S equal to U1, U2, all the way up to UK be a linearly independent subset of the vector space V. One needs to prove first that the set given by TU1, TU2, all the way up to TUK. So there are k vectors in this set, and we need to show that these set containing k vectors of the vector space W is a linearly independent subset. One needs to prove that the set this is linearly independent in W. Okay, so whenever we have to prove linear independence, we take an arbitrary linear combination of that set and set it to the zero vector of the underlying vector space. Okay, so let C1 TU1 plus C2 TU2 all the way up to CK TUK is equal to the zero vector of the vector space W, okay, where these coefficients of the linear combination C1, C2 all the way up to CK are scalars, are any scalars, any k scalars. We need to prove that they are identically zero. These scalars are identically zero. And that will prove that this set is a linearly independent set in the vector space W. Okay, so let me erase things here. Indeed, from linearity, of the transformation T, one has T of C1U1 plus C2U2 plus all the way up to CKUK. Okay, so let me write it first. So what we wrote initially was this, right? C1TU1 plus C2TU2 plus all the way up to CKTUK, and we set it to the zero vector of the vector space W. So using linearity, one has then T of C1U1 plus C2U2 plus all the way up to CK UK to be equal to the zero vector of the vector space W. We call it equation number 23. Okay. Now, since T is non-singular, this guy has to be the zero vector of the vector space V. From non-singularity, singularity of T, one has C1 U1 plus C2 U2 plus all the way up to CK UK to be equal to the zero vector of the vector space V. But the linear independence of S equal to U1 U2 all the way up to UK, we chose the set to be a linearly independent set in the vector space V. Remember? So from the linear independence of this set, it follows that all these scalars are identically zero. Implies the linear independence of this set in V implies C1 is equal to C2 is equal to all the way up to CK is equal to 0. They are all identically 0. Okay. So this argument shows that the image of this set S under the map T is indeed a linearly independent set in W. Hence, T of U1, T of U2, all the way up to T of UK is a linearly independent subset of the vector space W. Okay, so we have been able to prove one direction. Now the other direction, for the other direction, we assume that T takes linearly independent subset of V to a linearly independent subset of W. We have to prove that T is non-singular. So suppose now that T carries linearly independent subset linearly independent subsets of V to linearly independent subsets of the vector space W. Let U be a generic vector from the vector space V be non-zero. So that this guy, it's a singleton containing that non-zero vector. This is a linearly independent subset, linearly independent subset of V. Why? Because I take a linear combination, an arbitrary linear combination of this one vector that would look like this and set it to the zero vector. Okay, and since the vector U is non-zero, C has to be identically zero, right? Which means that this set is indeed a linearly independent subset of the vector space V. So now, according to the hypothesis, T acting on this non-zero vector U is a linearly independent linearly independent subset of the vector space W. Okay, why? Because T takes, according to the hypothesis, T takes linearly independent subset to to a linearly independent subset of the vector space W. T takes a linearly independent subset of V to a linearly independent subset of W. Okay, so and this guy will only be linearly independent. This set will only be linearly independent if TU is non-zero, right? That is, TU cannot be the zero vector of the vector space W. So one must have this. Okay. Uh, okay. Because it's clear that if it's a zero vector, then this set will be a linearly dependent set. Okay. In other words, so we just have seen that this is the case whenever um, this vector u is a non-zero vector in the uh, uh, in the vector space V. So this would imply this. Okay. So now uh, this statement would imply this. Now I take the contrapositivity of this thing, and that would mean that the negation of this statement would imply the negation of this statement, which means that Tu is equal to the zero vector of the vector space W would imply that the vector u is the zero vector in the vector space V, which means that this statement implies that T is non-singular. QED. Okay, now it's time to give you an example relating to non-singularity and invertibility of a linear transformation. Okay, so it's example 6. Let me erase everything. Example 6. Let F be a field and T be the linear operator on F squared defined by T acting on an element here in this vector space. This is naturally a vector space over F. Okay, T of x1 comma x2 is defined as x1 plus x2 comma x1. Okay. Now T acting on a vector like C times x1 comma x2 here. A vector addition is like this, right? x1 comma x2 plus y1 comma y2 is equal to x1 plus y1 comma x2 plus y2, and the scalar multiplication in this vector space is given by C times x1 comma x2 is cx1 comma cx2. Okay, the canonical vector addition and scalar multiplications in this vector space are given by these two expressions. Now, if I choose any vector of this form, c times x1 plus x2 plus y1 plus y2, and have it acted upon by t, then I'll get, according to this definition, this is nothing. So I'm rewriting this vector. So this vector is going to be an ordered pair. Um, cx1 plus y1 comma cx2 plus y2. Now according to this, it's going to be cx1 plus y1 plus cx2 plus y2 comma this guy, the first component, cx1 plus y1. Or in other words, let me rearrange the first entry, and that will leave me with cx1 plus cx2 plus y1 plus y2 comma cx1 plus y1. Okay, so therefore while, so this is one side, while um, c times t of x1 comma x2 plus t of y1 comma y2 is equal to, what is this? This is going to be x1 plus x2 comma x1, and this is going to be y1 plus y2 comma y1. Okay, so that we have, so we use the this relationship, this rule of scalar multiplication, and then we use this rule of vector addition to have the following: cx1 plus cx2 plus y1 plus y2 comma cx1 plus y1. Okay, so this is equal to this, and hence t of this vector c times x1 comma x2 plus y1 comma y2 is equal to c times t x1 comma x2 plus t of y1 comma y2, which establishes the linearity of this operator t on the vector space F2. Therefore, excuse me, t is a linear operator on the vector space F2. Now we will verify that t is non-singular. Let's see how we verify it. Verify that t is non-singular. Solve the system t of x1 comma x2 is equal to the zero vector of, uh, zero vector in the vector space F2. Okay, so we know that this is equal to x1 plus x2 comma x1. We set this ordered pair to the zero vector, and it gives us this system: x1 plus x2 is equal to 0 and x1 is equal to 0, and the solution is the the trivial, so x1, the trivial solution, x1 is equal to 0, and x2 is equal to 0. Okay, so t of x1 comma x2 is equal to 0 implies x1 comma x2 is equal to 0 comma 0, right? Which means that t is non-singular. singular. Okay, it also tells us that kernel of T is this zero vector only, right? Which means that T is non-singular. Okay. Now one also finds that T is onto. One also finds that T is onto. Let z1 comma z2 be any vector in the vector space F2. To show that z1 comma z2 is in the range of the linear operator T, one must find x1, x2 in F2 such that T x1 comma x2 is equal to z1 comma z2. That is, we are looking at this system. X1 plus x2 comma x1 is equal to z1 comma z2, right? So now the question is if such x1 and x2 can be found, right? So immediately from here we see that x1 plus x2 is equal to z1 and x1 is equal to z2. What does it mean? It means x2 is equal to uh, z1 minus z2. Okay, so we have been able to find x1 and x2 using z1 and z2. X1, sorry, uh, yeah, x1 comma x2 is equal to um, z2 comma z1 minus z2. z1 minus z2. So given a vector z1 comma z2, one can always find x1 comma x2 in F2 such that T of x1 comma x2 is going to be equal to z1 comma z2, which means that the whole of F2 is the range of T, meaning that T is onto. Okay, so this is a situation where T turns out to be non-singular and at the same time T is onto. But T non-singular does not necessarily mean that T is onto. This is a special situation when we have both these cases to be satisfied, both these situations to be fulfilled, satisfied. T is non-singular and T is onto. But whenever we have T to be non-singular, it is going to be one-to-one. We have seen that earlier. But it may fail to be onto in general when V and W are distinct vector spaces. Okay. But when V and W are finite dimensional vector spaces and um, uh, dimension of V and dimension of W are the same, then a lot of things start to happen, which generally don't hold when the dimension of V and dimension of W are unequal, given they are finite dimensional vector spaces. Okay? All right, so our next theorem focuses on this special situation when dimension V is the same as dimension W. Let V and W be finite dimensional vector spaces over the same field F such that dimension of V is equal to dimension of W if T from V to W is a linear transformation, the following are equivalent. So we abbreviate it as TFAE. 1. T is invertible. 2. T is non-singular. 3. T is onto. Okay. So we see that in this special situation, when dimension of V is the same as the dimension of W, non-singularity and ontolness are equivalent. Okay. All right. So here is the proof of this theorem. It follows from, it's a consequence of Rank-Nullity theorem. Let n equal to dimension of V is equal to dimension of W. Then from the Rank-Nullity theorem, we know that rank of T plus nullity of T is equal to n. Let me number it by 24. Now T is non-singular. T is non-singular implies kernel of T is trivial, right? Kernel of T consists of only the zero vector of the vector space V. T is a map from the vector space V to the vector space W. Okay, T is a linear transformation between these two vector spaces V and W defined over the same ground field F. So it implies that nullity of T is 0. Null space being zero dimensional, nullity of T is equal to 0. Now from equation 24 it follows that rank of T is equal to n, and n is equal to the dimension of W. Okay, and that implies that we immediately see that the range of T is the same as W, right? Because the range of T has dimension n and W also has dimension n. So range of T coincides with the vector space W. Range of T is equal to W. That means T is onto. So we started with T being non-singular and we arrived at the fact that T is onto. Okay. Now the other way around. When T is onto, one has range of T to be equal to W. That means since W is n-dimensional, we know that the rank of T is equal to n. Sorry, the rank of T is equal to n, which is the dimension of the vector space W, since T is onto. Now, again from 24, we arrive at the fact that nullity of T must be 0. Nullity of T is equal to 0. That is, kernel of T is going to be trivial, containing the 0 vector of the vector space V only. Okay, and it implies that T is non-singular. Okay, so one therefore finds that the second statement and the third statement of theorem 8 are equivalent, and in other words, they are simultaneously satisfied. Okay, and 2 and 3 together. T non-singular means T is 1 to 1, and T onto and T 1 to 1 together mean that T is invertible, right? So 2 and 3 together implies 1. 2 and 3 together imply 1, and hence 1 is equivalent to 2 is equivalent to 3. QED. All right. So at this stage, I'll take a break, and we'll have the rest of the lecture, which will involve in the rest of the lecture we will discuss a few things concerning the structure, the algebraic structure called group. Okay, thank you for attending this 5th segment.